So in section 2, we're going to apply the properties of rational exponents. And the good news for you is that the properties of rational exponents are the same as the properties of exponents, which you've already learned. But we are going to do some new things, and it's important that you understand the simplest form of a radical. You've actually already learned the simplest form of a square root. And the idea is the same as we discussed in 3.1, when the exponent in the radicand matches the index of a radical, then you can simplify the item and remove it from the radical. And then we have the idea of like radicals. These are a lot like terms. So you want to draw on the information of how you understand like terms in order to think about like radicals. Again, in working with problems that have exponents involved, we have this idea about velocity. I can measure the velocity in feet per second of a jet, can be approximated by this model that velocity is equal to 8.8 times the square root of L divided by A, where L is the lift in newtons and A is the area of the wings. So then we want to find the velocity of a jet when they supply us with the wing area and the lift, and we'll work that out in terms of how do we simplify these radicals. Okay, but first, the properties of rational exponents, you already have these. The product property, when I'm multiplying items with the same base, I add the exponents. The power property, when I take a power to a higher power, I multiply the exponents. The idea that the base of a power can be factored into two factors that have the same exponent. The idea of a negative exponent that creates an inverse. The quotient property, where I actually then subtract when I divide with powers with the same base. I subtract the exponent in the denominator from the exponent in the numerator. And the same idea that I can factor, when I could factor items that were being multiplied, I can also factor items that are being divided to separate them out. The only difference from when you learned these previously is that now the examples that you are given show exponents that are fractions as opposed to exponents that are whole numbers. But you'll notice that the properties did not change. The examples have changed a little bit. So how does this work in practice? So if I take a power to a higher power, I multiply the exponent. So I'll have 2/3 times 1/2. I would simplify before I multiply. So this is going to be 6 to the 1/3 power. Okay. This is a little different because they're not the same base, right? So if I would normally want to multiply these guys together with the same base, I could add the exponents. So if I want to simplify using the properties of exponents, I could make them the same, or so I have some choices here, right? I could say that this is 3 times 27 to the 1/4 power. That would be 81 to the 1/4 power, which would be equal to 3. That's accurate. Okay, but I could also rewrite 27 as a power of 3. So I could say this is 3 to the 1/4 power times 27 is 3 cubed, and that to the 1/4 power. So that would be 3 to the 1/4 times 3 to the 3/4. 1/4 plus 3/4 is equal to 3 to the first power. So I could do this problem either way I wanted. So I had a choice of using, in this case I used one property that basically says, when I have the same exponents I could multiply the bases together. I did, I simplified, and I got 3. Or, if possible, I rewrite this number to be a power with the same base as the other item. So I wrote it as a power of 3. And that then allowed me to add the exponents. Neither of these is better than the other. You should do either whichever one you feel is easier, or whichever one you spot when you're working on the problem, because you may notice one but not notice the other. Okay, so go ahead and practice this a little bit. Do problems 7 through 9, and then come on back to the lecture. Okay, now you've noticed we've taken these properties of properties you already know. They're right here, right? These properties are just this property and this property, where you're working with rational exponents. but they've gone and they've applied them to radicals. And you've already done this. You've already done this with the concept that you can factor apart the radicand. This is what we do when we simplify radicals. Okay, so these are not new properties. They're just repeats of the others. How do they work in practice? Well, I have these two radicals. They both have the same index. The index is 2. I could multiply them together. So I'll have the square root of 100, which is equal to 10. Okay, now when you're looking at these guys, they all have, again, the same index. So this could be, I could multiply the 9 and the 36. 9 times 36 is, what, 270 plus 54. Let me make sure I do that correctly. I don't want to make a mistake. So 9 times 36, 324. So that's 324. So the fourth root of 324 divided by the fourth root of 4. So if I take 324 and divide it by 4, right? This could all be the fourth root of 324 divided by 4, which is the fourth root of 81, which is equal to 3. Okay, if I didn't see that 81 is 3 to the 4th power, I could have used my calculator. I could have done 81 up caret, open parentheses, 1 divided by 4, close parentheses, enter, and it would do it for me. Okay, so go ahead and practice these guys. Do problems 16, 17, 19, and 20. Get a little practice with it, and then come on back. So when we want to work with radicals in simplest form, so we're looking for simplifying a square root, I'm looking again for perfect squares. So I have 36 and 2. Well, 36 is a perfect square, right? So this could be the square root of 36 times the square root of 2, which is 6 radical 2. Okay, so I started doing a factor tree, but I immediately bumped into a perfect square, so instead I just factored the perfect square out and simplified. Okay, when we take a look at these guys, 108 times 4. Now, I could multiply them together, but I don't see any real need for doing that. If I start looking, I'm going to do a factor tree for 108. Remember, I'm looking for factors that show up 3 times, right? That's what a perfect cube would look like in a factor tree. It would be a factor that shows up 3 times. So I'm going to start with the 108. I know it's 2 times 54, and then I'll have 2 times 27. It's 3 times 9 and 3 times 3. So far nothing has shown up 4 times, but then I also have this 4. 2 and 2. So I'll have 2, 2, 2, and 2. Those will create, oh, I'm sorry, I was looking for things to the 3rd power, my mistake. Right, so I'm looking for items that show up 3 times, not 4 times. Right, so I can pull out a 2. I can pull out the 3 shows up 3 times. And what remains is this 2. 2 times 3 is 6. Radical 2. Okay, so that's using, I basically revert normally to doing a prime factorization of the number. I'm looking for the 3rd index, so I'm looking for 1, 2, 3 occurrences of a number, 1, 2, 3, and then those guys come out as perfect cubes. All right, so you go ahead and practice that. Not yet, I'm going to show you something else. So let's do some other examples of simplifying. So this could be the square root of 49 times the square root of x squared times the square root of x squared times the square root of x. So what I pulled out was 1, 2, 3 perfect squares. So I'll have 7 times x times x times the square root of x. So this becomes 7x squared times the square root of x. Now you'll notice that if you think of the index being 2, if I took 5 and divide it by 2, I'd get 2, remainder 1. So you notice I brought out 2 x's. I got x squared, and my remainder, 1x, stayed inside the radical. Okay, so if that makes it a little simpler for you to do, you don't necessarily have to factor it out like this. I was being kind of explicit. All right, so there are a couple of ways to look at this problem. The first thing I want to do is I have an x in the denominator and an x in the numerator, so this x would come out of those 3, so that will leave me x squared. So the first thing I did was I simplified the fraction a little bit. If I had common factors in the 20 and the 9, I would go ahead and simplify those now. Okay, but now what I'm looking for is I'm looking for perfect squares that can come out of this. And it's important to remember that their location, numerator or denominator, will stay the same. So you'll notice 9 is a perfect square, so I would take the square root of 9 out. Z cubed could be z squared times z, so the z squared will come out as a z here. And in my radical, that leaves a z in the denominator, so I've cleaned up the denominator. 20 has a factor that's a perfect square, 4. Square root of 4 is 2, that comes out. I leave the 5 in. Square root of x squared is x, square root of y squared is y. So I wrote this a little awkwardly. So I have 2x, y, and I'm going to go ahead and put this radical 5 up here, over 3z radical z. And I would consider this fully simplified, except for the fact that I can't have a radical in the denominator. Ooh. So I'm going to multiply this whole thing by radical z over radical z. And then I'll end up with 3z squared in the denominator. And in the numerator, I'll have 2xy, but radical 5 times radical z would be radical 5z. Now I'm fully simplified. So I started and realized, oh, no, wait. I can't have a radical in the denominator of a fraction. All right, a couple more properties here. When I'm multiplying with the same base, so this is going to be x to the 1/4 plus 1/3. So I have the same base. That means I add the exponents. In order to do that, I'm going to need to have common denominators, right? So this is going to be x to the 3/12 plus 4/12. So this becomes x to the 7/12 power. Okay, and now I'm looking for items to the 3rd power. So I want to again show you, right? This could be x to the 5th to the 3rd power, because x to the 5th to the 3rd power would be x to the 15th. This could be y squared to the 3rd power, because y squared to the 3rd power would become y to the 6th. So again, when the index of the radical and the exponent of the power match, they cancel each other out, so I just get x to the 5th over y squared. Okay, go ahead and get a little practice. Do problems 45, 46, 53, and 57. And then come on back so we can, we'll do a couple more things and then solve that word problem. Okay, now the idea of like radicals, you're used to like terms, and like radicals work pretty much the same. So you can see that what I have here is I have radicals that are the same. So what you're used to doing is, if you know that if you had 2x plus 7x, that would equal 9x. Well, in this case, I replaced the 6th root of 3 with x. So this would really be just 9 times the sixth root of 3. What's easiest to think about is I had 2 of them plus 7 of them. That's going to equal 9 of them. But remember, you can only do this if the radicals are identical. So what would I do in this case? The radicals are not identical. Okay, the only way this problem could be simplified would be if there was some way for me to take 625, right, the third root of 625, and somehow simplify it so that it ended up being the third root of 5. Well, I know that if I continue to simplify just this part of the problem, this is 4 times the third root of 5 times the third root of 125, right? Because 625 is 5 times 125. I factored it because this is a perfect cube, right? 125 is 5 cubed, so that's going to come out. It's going to be multiplied times the 4, so I'll have 20 times the third root of 5, and now I'm going to bring this guy back down now that they match. 6 times the third root of 5, so 6 of them plus 20 of them will be 26 of them. Right, so that's working with like radicals. Let's do a couple more examples. Right here, the radical is the fifth root of x. They're already the same. 3 of them plus 9 of them would be 12 of them. That's pretty straightforward. Now here it's a little crazier, right? So the first thing I want to do is I want to start simplifying. Well, if I multiply, right, I'm taking powers to powers, so if I multiply the exponents, x to the fourth times 1/2 becomes x squared. Y to the first times 1/2 becomes y to the 1/2. X to the first being taken to the second power becomes x squared. And y to the 1/4 times 2, that becomes y to the 1/2. So you'll notice this is the same as that. I have one of them plus another one of them, that's 2 of them. Okay, so it works with rational exponents just like it works with radicals. It's all sort of the same. Okay, so go ahead and practice that. Do 38, 39, 64, and 65. Come on back and we'll wrap up the lecture. So in this word problem, I'm given a formula. That's nice. I need to figure out where to plug things in, right? You'll notice that A is the area of the wings. That's in the denominator of my fraction. I know I'm find the velocity, so I'm looking for the velocity. So the square root of L times, or divided by A. So in this case, lift was 1.4 times 10 to the 7th over 5.5 times 10 to the 3rd. So we're also going to do a little review here of scientific notation. Okay, so the first thing I want to do is I want to split the scientific notation into parts, because then I can work with the powers of 10 separately, and that's going to be easier. So velocity will be equal to 8.8 times the square root of 1.4 divided by 5.5 times the square root of 10 to the 7th divided by 10 to the 3rd. Well, 10 to the 7th divided by 10 to the 3rd is 7 minus 3 is 4. That's the square root of 10 to the 4th. And that is 10 squared. So over here I'll have 8.8 times, now I would simplify this if I could, but instead I'm just going to go ahead and I'm going to go ahead and do the division. Right? These can't be factored. So this is basically going to be 0.2545. When I actually take the square root, 8.8 times, this is going to be essentially 0.5045. I used a calculator to do that, times 10 squared. And then when I multiply this times 8.8, I'm going to get 4.44. And then I'm going to leave this in scientific notation, times 10 squared. This is what my velocity is equal to. Okay, so we had a little review of scientific notation, properties of radicals, and that wraps up 3.2.